Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to continue our discussion on curvilinear coordinate systems, and in particular we're going to be talking about some specific examples and applications of curvilinear coordinates and transformations. So let's start with a well-known system that has a lot of use in engineering. So this is Modeling Methods in ME. Let's start with the cylindrical coordinate system. Cylindrical coordinate system. One example of a curvilinear coordinate system to which we can apply these concepts of metric tensors and scale factors, if there's such a thing, to see if we can discern some information about it and be able to calculate some things, like differential of surfaces and chord length and so on and so forth. So let's look at the coordinate system and R, theta, and Z. And so the theta direction, again, is the tangential one. So this will be theta. And let's just make this, try to make this consistent. And right, so you get that. That's a cylinder. There's theta also surrounding around the axis C. And if we take a little bit of Z, for instance, call this dz, and take a little bit of R, and call this dr, and then we can project in this direction, and project in this direction. This right here will be the differential of surface perpendicular to theta, or ds2. 2 being the second dimension. Theta, remember, first dimension is R, second dimension is theta, third dimension is Z. If we take a little bit of theta, for example, d theta, and project in this direction, this being a little bit of R, so dr. This right here is ds perpendicular to Z, or ds3. And if we take, again, a little bit of Z, let's project it in this direction. Let's project it in this direction. And then this area here will be dsr, or ds1, the differential of surface perpendicular to the r axis, or ds1. Remember, in the orthogonal, in the cylindrical coordinate system, x1 is r, x2 is theta, and x3 is z. In the backward transformation, goes as, let's do it here, x is equal to r cosine theta, y is equal to r sine theta, and z equals to z. This is equivalent to saying y1 is equal to x1 cosine of x2, y2 is equal to x1 sine of x2, and y3 is equal to x3. Remember that x1, x2, and x3 are the curvilinear coordinates, while y1, y2, and y3 are the Cartesian coordinates. All right, so let's calculate the metric tensor. So the metric tensor Gij is given by the relationship dyk dxi dyk dxj. Remember that the repeated index k implies a summation, and this implies that we have a tensor relationship here because I and j are not repeated index, so we end up with 9 individual components. So essentially G11, for instance, would be dy1 dx1 dy1 dx1 plus dy2 dx1 dy2 dx1 plus dy3 dx1 dy3 dx1. So summation over k implied over 3 dimensions, and differentiating with respect to x1 and x1 for the metric tensor element 1, 1. All right. So if it makes it easier to visualize, we can say GRR is equal to dx dr dx dr plus dy dr dy dr plus dz dr dz dr. Remember, coordinate x1 is r, while coordinate y1 is x. So same thing. All right, so let's do it in the usual notation, RR, rather than doing the 1, 1 notation, 1, 2, and so on and so forth. So GRR is dx dr. So we take this relationship with respect to r. That would be the cosine of theta times the cosine of theta plus dy dr, y being r sine of theta. So that would be sine of theta, and dz dr will be this with respect to r, which is 0, plus 0 times 0. So that will be cosine squared plus sine squared. That will be 1. G theta theta will be equal to, well, dx d theta, dx d theta, dy d theta, dy d theta, dz d theta, dz d theta. So when we take this one and differentiate it with respect to theta, we get minus r sine theta minus r sine theta. When we take y and differentiate with respect to theta, we get r cosine theta, and when we take z and differentiate with respect to theta, we get 0 and 0. So this is r squared sine square of theta, r squared cosine square of theta. We can take the r squared out as a common factor, and so that will be sine squared plus cosine squared, which is 1. So this will be r squared. GZZ will be dx dz times dx dz, dy dz times dy dz, dz dz times dz dz. So this will be 0 times 0 plus 0 times 0 plus 1 times 1. So this is equal to 1. All right. Now we also need the off-diagonal components of the metric tensor. Let's start with gr theta, for example. And gr theta, let's write it out. It would be dx dr dx d theta plus dy dr dy d theta plus dz dr dz d theta. So gr theta, let's just box this. dx dr is the cosine of theta. Dx d theta is minus r sine theta. Plus dy dr is equal to the sine of theta. And dy d theta is equal to r cosine of theta. dc dr is equal to 0. And dc d theta is equal to 0. So here we have r sine of theta cosine of theta negative and r sine of theta cosine of theta positive. So this is 0. Likewise, grz will be dx dr dx dz plus dy dr dy dz plus dc dr dz dz. So grz is dx dr is the cosine of theta. Dx dz is equal to 0. Dy dr is the sine of theta. Dy dz is equal to 0. dz dr is equal to 0. dz dz is equal to 1. And that will give you 0. And as expected, the last one, which is the theta z component of the metric tensor, is equal to dx d theta dx dz plus dy d theta dy dz plus dz d theta dc dz. So g theta z is equal to dx d theta. It would be minus r cosine, minus r sine of theta. Dx dz is equal to 0. Plus dy d theta is r cosine of theta. Dy dz is 0. Dz d theta is 0. And dz dz is 1. So this all leads to 0. So as expected, as you can see, the off-diagonal terms are all 0. Recall, Gij is symmetric. That means that Gij is always equal to Gji. Okay. Now remember, this is G11. This is G22. This is G33 in the tensor. This one right here is G12. This one right here is G13. And this one right here is G23, which is exactly the same as G32. This one is G31 and this one is G21 because the tensor is symmetric. So the metric tensor Gij is equal to the 9 components 1 r squared or 1 0 0 0 0 0 and 0. Or you can express this in terms of the curvilinear coordinates. Remember that r is equal to x1. This will be 1 0 0 0 x1 squared 0 0 0 1. Same thing. Remember the r, again, equivalent to x1. Now, because Gij is diagonal, then system is orthogonal. So the curvilinear system that led to this metric tensor is an orthogonal coordinate system. And that's expected because we know for a fact that the cylindrical coordinate system is orthogonal. So if we would have gotten something different than a diagonal tensor, then we made a mistake in the calculations. All right. Now, because the system is orthogonal, then scale factors H1, H2, H3 exist. So H1, which is the same thing as HR, is equal to the square root of G11, which is equal to the square root of GRR, which is equal to 1. H2, which is equal to H theta, is equal to square root of G theta theta, which is equal to, 2, square root of G theta theta, is equal to R. So the square root of R squared is R, or we can call it X1 or R. And then H3, which is equal to HZ, which is equal to the square root of G33, which is the same thing as the square root of GZZ, is equal to 1. So again, these scale factors only have a meaning because the system happens to be orthogonal. The metric tensor is a diagonal tensor. So, in summary, X1 is equal to R, X2 is equal to theta, X3 is equal to Z, GRR is equal to 1, G theta theta is equal to R squared, and GZZ is equal to 1. And therefore, there are such things, scale factors, HR is equal to 1, H theta is equal to R, and HZ is equal to 1. Okay? Now, with that information, we can calculate things such as, for example, the differential arc length. So the differential arc length, dl, remember, dl square is equal to GII dxi squared. This happens to be the case for orthogonal systems, which is dr squared plus r squared d theta squared plus dz squared. So if we wanted to calculate the length of anything in the cylindrical coordinate system, it will be the integral from P1 to P2, from between 2 points, of the differential arc length, which is the integral from P1 to P2 of dr squared plus r squared d theta squared plus dz squared. And how do we integrate something over differential squared? Well, we need to parameterize. So we parameterize the line from P1 to P2 such that we get R as a function of some parameter C, theta as a function of some parameter C, and Z as a function of some parameter C. And therefore, we end up with the length being the integral between C1 and C2 of the square root of the R dc squared plus R squared d theta dc squared plus dc dc squared, all of these times dc. So we implicitly here use the chain rule just by saying that, well, dr is equal to dr dc dc. So let me write this here, see if I can fit it. The differential of R is equal to dr dc times dc. The differential of theta is d theta dc times dc, and the differential of z will be equal to the differential of z with respect to c dc. So we plug that in to here, and we automatically get this expression as a function of the parameter c, and where we have these derivatives, or the squares of the partial derivatives of each of the components. These are actually not partial derivatives. These are total derivatives because this is a function of a single parameter. There will be partial derivatives of each of these parametrizations is with respect to more than one parameter, which is not the case if we're talking about a line in space, in this case in cylindrical space. Another example would be, well, what if we need to calculate the area, for example? Remember that the surface differentials have to do with a Jacobian of a transformation. So in cylindrical coordinate systems, dsr, which is ds1, is equal to h2 h3 dx2 dx3, which is r d theta dz. ds theta is equal to ds2, which is h1 h3 dx1 dx3. That's dr dz. And dsz is equal to ds3, which is equal to h1 h2 dx1 dx2, which is, well, h2 is equal to r dr d theta. All right. So those are the surface differentials perpendicular to each of the axes, as we noted here. So this will be DSR will be the size of these differential, this shaded area right here, and that is r d theta dz. ds theta will be the size of this, is a perfect square, so it's directly dr dz. And dsz will be the size of this shaded area right here, which is not perfectly square, and therefore has the r in the middle there. All right. So this one goes here. Now, what if we need to calculate, for example, EG? What is the perimetral surface of a cylinder of radius r and height h? Well, in order to do that, the surface that is perpendicular to r, and we're talking about the perimetral area of the cylinder, that doesn't include the caps or the bottom, will be the integral over the surface of ds perpendicular to r. So basically we'll be essentially adding up all the surface around the perimetral area, dsr. So that would be the integral of dsr, which is r d theta dz, when r is equal to r, because we're only doing that at the perimeter, from theta from 0 to 2 pi, and z from 0 to h. So this comes out right out of the integral. There's no r integration here, and that is directly 2 pi rh. So that is the perimetral surface area of a cylinder. All right. So we can also calculate, well, using the same approach, what would be for example, the surface area of the top, and that's the area of a circle. We'll certainly get pi r squared if we take dsz, which is this one here, r dr d theta, and integrate from 0 to r, from 0 to 2 pi. We get pi r squared. You can try it. All right. So let me move to another page. I want to talk about another coordinate system to exemplify here, the spherical coordinate system. Oh, before I do that, let me go back and also calculate the volume, for example, of the cylinder. So before I go into spherical coordinates, so we talk about the surface differentials. Now the volume differential. So that would be dV is equal to h1, h2, h3 times dx1, dx2, dx3. And therefore, the surface differential would be r dr d theta dz. So what is, as an example, what is the volume of a cylinder of radius r and height h? So same thing. So the volume of a cylinder will be the integral over the differential of volume, which is equal to the integral of the integral of r dr d theta dz, where r goes from 0 to r, theta goes from 0 to 2 pi, and z would go from 0 to h. So if I integrate r dr, I'll get r squared over 2, and actually this will be from 0 to 2 pi. So this will be, oh, you can carry out this integration very easily. This will be r squared over 2, evaluated between 0 and capital R. Then this will be theta, evaluated between 0 and 2 theta, 2 pi, I'm sorry, that's 2 pi r squared over 2. So the 2 and the 2 in the denominator cancel out. And then the integral over z, which is z, evaluated between 0 and h. So the volume of a cylinder is pi r squared h. And we knew that. But it comes right out of the differential volume. All right. So let's look at another common curvilinear coordinate system, known as a spherical coordinate system. And in the spherical coordinate system, let me try to illustrate how it goes. So this will be z, x, and y. And you have to use your imagination to know that this is a sphere, sort of. And let's use this line here to show that, well, this is a surface of a sphere, and this will be a point on the surface of the sphere. This is radius r. This is what's called the azimuthal angle. I'm sorry, this will be phi. I'm sorry, theta. And the angle of the projection, so I'm going to project this point on the sphere to the plane xy, and the angle with respect to the x-axis, to the projection of the point onto the plane xy, is the equatorial angle, phi. So phi is now the equatorial angle, what we used to call theta before in the cylindrical coordinate system, and now theta, again, this will be theta, is the angle with respect to the z-axis, the azimuthal angle. So again, r, so x1 is r, is the radius, x2 is equal to phi, which is the equatorial angle, and x3 is theta, which is the azimuthal angle. The backward transform So the backward transformation of the system goes like this. X is equal to R cosine of phi sine of theta. Y is equal to R sine of phi sine of theta. And Z is equal to R cosine of theta. Okay, so this is pretty easy to see. The coordinate Z, for example, would be R is the hypotenuse at any point within the sphere, not just on the surface, any point within the sphere. And the projection of that angle into the z-axis is r cosine of theta, because this is an adjacent angle. That will be z. And if I project r over to the xy plane, right, that would be r sine of theta. And then I can find the x-axis by using the adjacent angle cosine of phi, or the complement of the adjacent angles is sine of phi for the y-axis. Okay, so this is a transformation between the coordinates and the spherical coordinate system, defined like this, and the Cartesian coordinate system. Again, this will be also denoted as y equals to x1 cosine of x2 sine of x3. y2 is equal to x1 sine of x2 sine of x3. And y3 is equal to x1 cosine of x3. All right, that's the backward transformation. Again, GRR, let's find the metric tensor. GRR is equal to dx dr dx dr plus dy dr dy dr plus dz dr dz dr. So GRR is dx dr. That would be cosine of phi sine of theta, and I'm just going to square that up. If not, just let me write it out. dy dr would be sine of phi sine of theta times sine of phi sine of theta. This one doesn't go here. This parenthesis. And then the third one will be plus dc dr, which is a cosine of theta, times dc dr, which is a cosine of theta. So GRR is equal to, I can take, see, this is the sine square and the sine square, so I can take the sine square as a common factor, multiplying the cosine of phi square and the sine of phi square, and this is a cosine square of theta. So I took the common factor, the sine square, and I got that GRR is equal to 1. So cosine of phi, cosine square of phi, sine square of phi is 1, and then the sine square of theta, cosine square of theta is also 1. So it all cancels out to give you 1. All right, so let's look at the next one. G theta theta, or phi phi, which is the second curvilinear coordinate. G phi phi would be dx d phi plus dy d phi d phi plus dc d phi dz d phi. So G phi phi will be, so dx d phi is minus r sine of phi sine of theta times minus r sine of phi sine of theta. So, and then dy d phi would be r cosine of phi sine of theta, r cosine of phi sine of theta. And dz d phi is equal to 0, and dz d phi is equal to 0. So g phi phi. So here I can take r squared as a common factor, and I can take sine square of theta as a common factor, and I get this is minus and minus is a positive, so I get the sine square of phi, and I can take this sine square here as a common factor and the r square as a common factor, plus the cosine square of phi. So as you can see, this is 1, and then g phi phi is r squared sine square of theta. R squared, the sine square of theta. Finally, g theta theta, which is dx d theta dx d theta plus dy d theta dy d theta plus dz d theta dz d theta. Let's calculate this out. G theta theta would be, so dx, let me bring this down, dx d theta is equal to r cosine of phi cosine of theta times r cosine of phi cosine of theta plus dy d theta, that would be r sine of phi cosine of theta times r sine of phi cosine of theta. That would be this one with respect to theta. And then finally plus dc d theta, which will be minus r sine of theta minus r sine of theta. All right. So here, g theta theta is equal to I'm going to take r squared and the cosine square of theta as a common factor from this one and from this one. And then this one has the cosine square of phi, and this one has the sine square of phi. And this is plus r squared times the sine square of theta. And as you can see, this one is 1. And then I can take the cosine square and the sine square with r squared as a common factor. And at the end of the day, what I get is that g theta theta is equal to r squared. Okay, so those are the 3 diagonals. We can show, and I'm not going to go through the process, we can show that gr phi is equal to gr theta, which is equal to g theta phi, which are equal to 0. So the metric tensor gij is equal to or this is 1 1 0 0 0 r squared sine square of theta 0 0 0 r squared. Right? So diagonal means that system is orthogonal. All right? So essentially GRR is equal to 1 means that HR is equal to 1. G phi phi equal to r squared sine square of theta implies that h phi is equal to r sine of theta. And g theta theta equals to r squared implies that h theta is equal to r, the square root of that. Now remember, these scale factors only exist because the system happens to be orthogonal. If the system were not orthogonal, the scale factors do not have a meaning. All right. So we calculated this metric tensor for the spherical coordinate system, and found out that it was diagonal, and since the metric tensor is diagonal, the system is orthogonal. So now we can calculate the surface differentials. DSR, which is h phi, h theta, d phi, d theta. So this is a surface differential perpendicular to the r axis, is equal to r squared sine of theta, d phi, d theta. So it's h2, h3, dx2, dx3. ds phi, which is equal to hr, h theta, dr, d theta, will be r times dr d theta, and ds theta, which is equal to hr, h phi, dr, d phi, is equal to r sine theta, dr, d phi. We can, for example, calculate what is the surface area of a sphere of radius r. What is the surface area of a sphere of radius r? So what we'll be doing is just at r equal big R, we'll be integrating this surface differential, dsr, about all the angles, all the possible azimuthal and equatorial angles. So the surface of a sphere of radius r is equal to the integral over the surface ds perpendicular to r. Differential surface perpendicular to r. Its integral over a surface is the integral over the integral of r squared sine theta, this one here, d phi, d theta, where the limits of integration for phi go here, and the limits of integration for theta go here. In the phi direction, remember the equatorial angle, this will be from 0 to 2 pi. And in the azimuthal angle, theta, and theta, the azimuthal angle, we only sweep from 0 to pi. In the equatorial angle, phi, we sweep from 0 to 2 pi, the entire circumference. Well, in the azimuthal angle theta, we only sweep from 0 to pi to complete a full sphere. If we were to sweep theta from 0 to 2 pi, we'll be actually rotating over 2 full spheres. So we have to be careful with that. All right. So, and this is r evaluated at big R. There's no integration with respect to r, so we don't have to worry about that. We just evaluated at r. So, as r is equal to, well, let's just take this integral with respect to phi. It will be phi, that will be 2 pi r squared times the integral from 0 to pi of the sine of theta d theta. And that will be equal to 2 pi r squared times minus the cosine of theta from 0 to pi. The cosine of pi is minus 1, and the cosine of 0 is 1. So minus 1 plus 1 is equal to 2. So the surface area of a sphere of radius r is 4 pi r squared. You can look it up on Google, and that is the surface of a sphere. The surface area of a sphere. We can look at the volume differential. Volume differential. And remember, there's a single one, and for an orthogonal system, All right. We had a jump there in the recording. So a volume differential, there's a single one. It's H, R, H phi, H theta, dr, d phi, d theta. And that's only true because the system happens to be orthogonal. If not, we had a combination of the elements of the metric tensor. So the surface or the volume differential will be r cubed times, so it will be r squared. So hr is equal to 1, h phi is equal to r sine theta, and h theta is equal to r. So it's r squared sine theta times dr, d phi, d theta. So let's use that to calculate the volume of a sphere. E.g., what is the volume of a sphere of radius r? So the volume of a sphere is equal to the integral over the volume, differential volume, which is a triple integral of these differential of r squared sine of theta, dr, d phi, d theta, where r goes from 0 to r, phi goes from 0 to 2 pi, and theta goes from 0 to pi, half a rotation in the azimuthal direction. So if we integrate this, note that we first integrate over r, that we get r cubed over 3. Then we integrate over phi, which is just phi times 2 pi. So that will be 2 pi r cubed over 3. And then we integrate the sine of theta over theta. And at the end of the day, we'll get that the volume of a sphere is equal to 4 pi r cubed over 3. It all comes from this expression right here. All right, so that's some examples of some implementation of two well-known orthogonal coordinate systems, the cylindrical and the spherical, and I use those in particular in these examples because these are used widely in engineering and science. Cylindrical coordinate systems, anytime there's anything having to do with pipes, we try to frame it in cylindrical coordinate system and try to make it axisymmetric if things actually do not swirl. And anytime there's a phenomenon that propagates spherically, like sound, for example, or like electromagnetic waves, or anything that propagates spherically, then we try to frame the space into a spherical coordinate system, so that makes the calculations a lot easier to do. But there are times where that's not possible, and then we have to resort to the generic form of the curvilinear coordinates. I'm in trouble with this piece of paper again. So what happens when we apply these to two-dimensional curvilinear coordinate systems? And numerical modeling. That's what we call meshing. Anytime we use a local coordinate system to mesh a surface or mesh a domain so that we can apply finite elements or finite volumes so that we can solve a field problem, we are doing a coordinate transformation from a global to a local space. And let me start by looking at a simple case in which we just take the XY coordinate system. Let's do it here. We're going to be doing this in 2D just to illustrate it, but this also applies in 3D, obviously. And let's say that we want to define a rotated coordinate system. UV. And that rotated coordinate system, let's say this function here, or this line is defined by y equal x. Well, this one is defined by y equals minus x. And let's try to square these with another line that is perpendicular to this one, parallel to this one. And we call this line y equals x minus 1. So it's the same slope as this one. So these two are parallel, but this one actually intersects the y-axis at minus 1. And let's call this line right here line y equals minus x plus 1. So same slope, but intersecting the y-axis. So this one intersects the y-axis at minus 1, and this one intersects the y-axis at 1. And the intersection of these make up that shaded area. And when we look at the transform coordinate system, we're looking at something like this. This is the so-called curvilinear coordinate system. Even though it's not curvilinear, it's perfectly orthogonal. As you can see, this axis is orthogonal to this one. But this one actually happens to be rotated from the y-axis, and this one rotated from the x-axis. So in this coordinate system, this will go from 1 to 1. This shaded area here is the area of interest. So this will go from 0 to 1, and this will go from 0 to 1. This is the line y equal x. This is the line y equals minus x. Well, this is the line y equals minus x plus 1, and this is the line y equals x minus 1. So the forward transformation goes as u is equal to x minus y, while v is equal to x plus y. Okay? So if we want to refer to any point in the new coordinate system uv, in terms of its location in the xy system, and the global coordinate system is x minus y, well, this one will be x plus y. And likewise, we can solve this backwards. So the backward transformation x as a function of u and v is such that if y is a function of u and v, so we got to solve a system of two equations with two unknowns. U plus v is equal to 2x, v minus u is equal to 2y. So we add these two and we subtract these two, and by such we eliminate the x and the y from these two equations, and then we solve x is equal to 1/2 of u plus v, while y is equal to 1/2 of v minus u. That's the backward transformation. So we can calculate an area in the xy system, and that area will be identical in the uv system, because the uv system, well, there's an invariant on this transformation. So we need a Jacobian times du dv. Okay? And the system, the system in the uv plane, the system is perfectly square, and the limits of integration are from 0 to 1. So the surface area transformation in 2D is equivalent to a volume transformation in 3D. So remember, we're talking about a two-dimensional coordinate system. And in two-dimensional coordinate system, the Jacobian will be equivalent to the Jacobian of the volume transformation in 3D, which is the determinant of this tensor dy dv. Right? So we take the determinant of the metric tensor, and in this case dxu dx du is equal to 1/2, dx dv is equal to 1/2, dy du is equal to -1/2, and dy dv is equal to 1/2. So the Jacobian is the determinant of the tensor 1/2, 1/2, -1/2, 1/2, which essentially takes the diagonal and subtract the multiplication of the off diagonal. So we multiply these two and subtract the multiplication of these two, which is equal to 1/2 times 1/2 minus 1/2 times -1/2, and that's equal to 1/2. So the area of the rotated frame of reference is the integral from 0 to 1 of 1/2 du dv, and the area is just simply 1/2. So this helps you calculate, for example, in this case, the area, or if you need to integrate anything over the area, any quantity over the area, for example, a flux of a field, heat flux, for example, integrate over an area to calculate the amount of energy that goes out, or if you need to calculate the mass flow rate, so the velocity times the normal vector in the direction of the particular surface area. And you can do it in this rotated coordinate system. It would actually become a lot easier because the integration will be as simple as doing integration from 0 to 1 and from 0 to 1. This is a trick that we can play with curvilinear coordinates, even though these coordinates are not technically curvilinear, because this is just a rotation of the original coordinates. But if, for example, we needed to find the area of that shaded region, instead of trying to integrate this function and this function from this limit of integration to this limit of integration, and so on, which will be a little bit complicated, we can just rotate the system, okay, scale the system from 0 to 1 and 0 to 1, and then we just basically be integrating over a square, and all we need is a Jacobian of the transformation from a differential of area in the global coordinate system to an area in the UV system, or vice versa. All right. Now, this is just an example of how we can use curvilinear coordinates to help us, for example, in an integration process. This might come handy in some applications, but what I really wanted to get at is the implementation of generalized, we're talking about generalized curvilinear coordinate systems in, for example, finite element method, FEM. Because say you have in the global XY coordinate system, and again I'm going to illustrate this with a 2D example, but this applies as well to 3D cases. So let's say that we have this domain over which we want to calculate, I don't know, the stress field and the deformation field, given some constraints and loads. And in order to do that, we're going to mesh it. So we perform a meshing process so that we can break this domain up into multiple little elements, and that element we're going to call E, element E. All right. If you notice, that local coordinate system might be different at every element because these curves might not actually be parallel to each other or perpendicular to each other. That would be nice in a very uniform grid, but normally we don't have the luxury of producing a uniform grid because the domain itself is irregular. So what we need to do is, well, go from the global coordinate system xy, in which we look at a single element, in a coordinate system, and in numerical methods, the coordinates xi and eta are used commonly. So in this coordinate system, let's say that we have an element like this. As you can see, this will be different for every element, and the element is defined by some nodes: 1, 2, 3, 4, where each node has coordinates y1, x1, y1, x2, y2, x3, y3, and x4, y4. And somehow we're going to, given that information, that particular element is defined by these 4 nodes, and each of those 4 nodes have those coordinates x1, y1, x2, y2, x3, y3, and so on and so forth. We're going to produce a forward transformation and a backward transformation into a system. Let me use red. Into a local system xi eta that goes from 1 to -1 in the eta direction and the xi direction, and from -1 to 1 in the eta direction. So that system, we're going to try to map into this square. This is a 2 by 2 square. All right, where this point is -1, -1. This will be node number 1. So node number 2 here, we're going to try to map into point 1, -1. Node 3, we're going to try to map into a node 1, 1. And node 4 is mapped to a point -1, 1. All right, so let's see if we can come up with that transformation in general, using this information only, that the element E is defined by these 4 nodes, and these are the coordinates of these 4 nodes. So we're going to map it, whatever the orientation of that element, whether these 2 lines are perpendicular to each other, parallel to each other or not, is going to produce the square in the local coordinate system. And this might be an orthogonal transformation or not, depending on whether these axes are orthogonal to each other or not. So a 4-noded finite element in 2D is called a bilinear element with forward transformation x of psi and eta is equal to the summation from I equal 1 to 4, this being the number of nodes, of the coordinate of node I, the x coordinate of node I, times some basis function of psi and eta. So the ith basis function, y, of psi and eta is equal to the summation from I equal 1 to 4 of the y coordinate of the ith node ni psi, and eta. And by the way, these are backward transformation. It's backward transformation. We're going from eta and psi and eta to x and y. And these are the transformations that we need in order to calculate the elements of the metric tensor. Okay, these functions, ni, n1, n2, n3, and n4, are called the basis functions. These are the functions that make it possible to actually map from here to here. Where ni, psi, and eta are the bilinear basis functions. These are called basis functions because they obey the following property. And it's a very powerful property because when I take the ith basis function and evaluate it at the jth node, I get 1 if I is equal to j, and I get 0 if I is different than j. Okay, so this will basically allow you to say when you're trying to use these basis functions to map these 4 nodes in the global coordinate system to these 4 nodes in the local coordinate system, when we evaluate at -1 and -1, I should get 1 for the basis function 1, and I get 0 for the other ones. So with that information, then I can construct, then let me write them down so that this makes sense. Then these are, so basis function 1 of psi and eta is equal to 1/4 of 1 minus psi minus eta plus psi times eta. And 2 of psi and eta is equal to 1/4 of 1 plus psi minus eta minus psi times eta. And 3 of psi and eta is equal to 1/4 of 1 plus psi plus eta plus psi times eta. And n4, psi and eta is equal to 1/4 of 1 minus psi plus eta minus psi times eta. Okay, so notice that if I evaluate, for example, n1 at node number 1, which is -1, -1, if I plug psi equal -1 and eta equals -1, it will go to 1. But if I plug any of the coordinates of the other 3 nodes, any of the coordinates of the, like 1, 1, for example, if I plug in 1 and 1 for psi and eta, I'll get 0. If I plug in -1 and 1 for psi and eta, I'll get 0. If I plug in 1 and -1 for psi and eta, I'll get 0. And same thing goes for the second basis function. If I plug in the coordinates of node number 2, 1 minus 1, 1 minus 1, I'll get 1. But if I plug in the coordinates of any of the other 3 nodes, I'll get 0. And that's why they're called basis functions. And this will automatically interpolate, therefore, notice that if I take x of psi and eta, so if I use the expansion, x of psi and eta is a summation from 1 to 4 of each of the nodes. So it's x1 divided by 4 times this relationship of psi 1 plus x2 divided by 4 times 1 plus psi minus eta minus psi and eta plus x3 divided by 4 times this basis function, well, the 4 is also part of the basis function, plus x4 divided by 4, 1 minus psi plus eta minus psi times eta, right? And that would actually allow you to map the x-coordinate anywhere in the square you can map into the global xy coordinate. At least the x coordinate, you can do the same thing for the y coordinate. So these basis functions serve to interpolate the geometry to the local coordinate system psi eta. And they can also be used to interpolate the values of the field variables to the local system. I.e., for example, if a field variable is, say, the temperature, and you want to interpolate it into the local system, it will be the same thing. It will be the summation from 1 to 4 as the temperature at every one of the 4 nodes times the same basis functions as a function of psi and eta. And then you can perform integration, for example, if this is part of the differential equation, and so on and so forth. Similarly, biquadratic basis functions may be derived to transform global curved quadrilaterals into squares in the local system. So we can come up with higher order elements. So, for example, if we have x and y, and let's say that we have an element that looks like what color combination did I use before? So let's say that this element looks like this. So we have an element that happens to be curved like that, and this is node 1, node 2, node 3, node 4. This will be node 5, node 6, node 7, and node 8. So the coordinate eta will go through here, and the coordinate phi will go to here. So we'll produce a forward and a backward transformation, so that in this coordinate system, with these curved element will look like a perfect square. In the psi eta coordinate system, the square again will go from -1 to 1 in psi, -1 to 1 in eta, and the nodes will map out identically. 1, 2, 3, 4, 5, 6, 7, and 8. Where in this coordinate system, this is -1, 1. This is 0, -1. This is 1, -1. The coordinates of node 6 are 1, 0, 1, 1, 0, 1, -1, 1, -1, 0, and -1. So these the 8-noded biquadratic finite element map out to the global coordinate system, the backward transformation, as x, psi, and eta equals to the summation from I equal 1 to 8 of xi and I, psi and eta. Y of psi and eta is equal to the summation from I equal 1 to 8 and why not if this is a three-dimensional system. So for example, this can actually be curved also in the z-axis, right? So we can be talking about the surface of a three-dimensional shape. Z can also be mapped into this two-dimensional square by the same type of interpolation. Same exact one. For example, integration of a field variable, let's say now we call it f of x, y, and z on the surface S and global coordinates x, y, and z will reduce to an operation. So we have an integral over the surface of f of x, y, and z, which we need to perform because it's part of the differential equation that you're trying to solve. There's a generation term or some kind of quantity that goes to the surface. Again, a heat flux, and we need to balance the energy. It's all part of the operations inside, under the hood of any solver. Then this will equate to an integral between minus 1 and 1 of f, and then x will go as x of psi and eta, y of psi and eta, z of psi and eta, some Jacobian of the transformation psi and eta, d psi, d eta. So it will reduce to an integral from minus 1 to 1, which is a simple integral, where the Jacobian of the transformation is now the square root of g psi psi, g eta eta minus g psi and eta. Remember, this coordinate system is not orthogonal, so we have to use the full elements of the full set of elements of the metric tensor, where g psi psi, for example, is dx d psi square, dy d psi square, dz d psi square, g eta eta is equal to dx d eta square plus dy d eta square plus dz d eta square, and g psi eta is equal to dx d psi dx d eta plus dy d psi dy d eta plus dz d psi dz d eta. And there's the three elements of the metric tensor. Remember, the metric tensor continues to be symmetric. So the Gij is equal to g psi psi, g psi eta, g eta psi, g eta eta, such that g psi eta is equal to g eta psi. It's symmetric. It's not diagonal, but it's symmetric. So we can perform this integration, which is crucial to any under-the-hood algorithm that solves numerically a set of equations of any field problem, where there's any kind of conservation going on, conservation of momentum in the dynamic solver, a vibrations problem, conservation of energy, conservation of angular momentum, conservation of mass, etc., etc. They're all confined to these type of integrals that need to be performed under the hood, because under the hood, finite element method is an integral method, such as the boundary element method is also an integral methodology that requires these types of integration that can only be performed in local coordinate systems by knowing how to transform between curvilinear coordinates and the global coordinate system. So this is it for today. I just wanted to give you some compendium of possible applications that these curvilinear coordinates can take on. What will be relevant to us in this class is what we're going to be doing in the next lecture, which is actually learning how to implement the vector operators, such as the curl and the gradient and the divergency and the Laplace, in general curvilinear coordinate system, more importantly in orthogonal curvilinear coordinate systems. These stuff that I went over today, these applications to meshing, for example, is applicable to numerical modeling, and we go in depth on this on a follow-up class to this one. It's called ME 601. It's Advanced Modeling Methods in Mechanical Engineering, where we go in depth into finite elements, boundary element, meshless methods, and all these kinds of numerical modeling techniques. So thank you for your attention, and I'll see you next lecture.